right, here we have rotational motion video number 5, dealing with rotational momentum. The symbol for rotational momentum is L, just a fancy L. Momentum is equal to your rotational inertia and your rotational speed. So your inertia is your resistance to motion, and the speed tells you how fast you're going. So just like before, regular momentum was just equal to mass times velocity. Your mass is your inertia. So in essence, it's the same thing, but just going around in circles. This is just like regular momentum, but cooler. The rotational momentum of a rotating object will remain unchanged unless acted upon by an outside force. So basically, what this is saying is whatever your starting rotational momentum is going to be your final momentum, unless acted upon by an unbalanced torque, force times a distance. So your force times your distance is going to apply a torque, causing you to spin faster or slower with a different angular acceleration. But if your rotational inertia changes, or your rotational speed, the other one will have to change inversely proportional. So L equals I omega. Let's say in your problem, I goes down. What would have to happen to W? Would go up. L stays the same. Your rotational momentum does not change unless acted upon by an outside torque. Let's look at a problem. Figure skater starts off with a radius of 0.45 meters. She's spinning at a rate of 30 radians per second, then pulls her arms, hands in, and legs to have a new radius of 0.25. So what is her new speed? We can consider her a solid cylinder. So L is going to be the same, is equal to I omega. So we say I omega 1 is equal to I omega 2. 1/2 mr squared W is equal to 1/2 mr squared W. Section 1, section 2. Now, doesn't give you a mass. Don't get hung up on these types of problems. Because you're setting them equal to each other, guess what goes away? The 1/2s and the masses. So this is how we want to solve, is write out the equations, see if things start to cancel out. 9 times out of 10 they do, especially stuff that you're not given. So then you have r squared over omega divided by r final squared equals W. 0.45 squared times 30 rads divided by 0.25 squared. And you plug that all into your calculator and you get 97.2 rads as your answer. So the key is L stays the same. If I goes up, W goes down. All right, there's more to rotational momentum. There's another way to solve. Not only does L equal I omega, but it also equals mvr. So if I have a small mass, even a big mass, with a straight line velocity, and then it hits an object that is a radial distance away from the axis of rotation, this is an alternative way to solve for rotational momentum. Let's look at what a problem would look like. So a 0.5 kilogram ball with a speed of 4 meters per second hits a stationary rod that is 2 meters from the axis of rotation. What is the rotational momentum of the ball rod system after they collide and stick together? Oh, that sounds like so much work. But the momentum before equals the momentum after. So all I have to do is find the momentum for this little ball over here. So here's my little ball. He's traveling Here's this rod. It's going to start to pivot and turn after the scenario, but I don't even care about that. I just want to know L is equal to mvr. So the mass is 0.5, 4 kilogram ball. This is 2 meters long, so that's the thing it's going to make to spin. So 2 times 4 is 8, and half of that is 4. So what's the rotational momentum of the ball rod system after they collide and stick together? Whatever it was before. And before, it was 4. So that's all for rotational momentum. Great job, guys.